Please note that while we're working to assist students to catch up and to resubmit for some things, I am going to be posting the Module 3 initial assessment, the first version of the Module 3 assessment, before the day is out. And we need everyone to log their first attempt by the start of class, 10 a.m. on Friday. That's critically important. That's a basic, hard, fast deadline in order for us to continue to inch our way forward with the rest of the material, so we get to the really good stuff at the end where you're building your own computer systems and servers. We have to take care of the other components and digital infrastructure ahead. So we need to make sure that we log our first attempt by Friday at 10 a.m. If you have not yet finished your logic gate submission, I will be posting a solution for the logic gate assignment, which means that the opportunity to complete this assignment will evaporate for any of you who have not yet submitted. Once we post the solution, basically you don't have a window to submit something on your own before we post that solution. When we post the solution, it's important for you to look at your own submission and look at the solution and see if they track. If they do not track, it would be good for you to send me an email to request a screen share so that we can walk through some things and make sure everybody's in a good place with this assignment. You will see something like this assignment over and over and over through the end of the modules, because you're going to get more practice at this and you get better and better at it the more you do it. So this is the first of several. Once again, we need to make sure we log the credit for this for everyone before we post the solution. Does that make sense? Does everybody understand why we have to close out this assignment and that you would not have any additional opportunity to submit after the next 24 hours? Everyone good? Are there any questions? Yes. Are there any questions?
Morning. It's not a question, but Sean Day is at a doctor's appointment right now, so he might not be able to make it to class today.
I really appreciate you mentioning that, because what I'm going to do is, if you have Sean Day, just send an email reminder. I'll excuse that absence, okay?
Okay.
It's a good idea for folks to just send a text or an email on their own, but he has notified me by proxy through you, so that's fine. I just need some little blurb from him, and then we can administratively qualify that, okay? Can you do that for me?
Yeah, no problem.
Okay, great. Yeah, and you know, if he's in a lot of pain, you can wait until those pain meds kick in before you talk to him about that. In any case, yeah, there you have it. Okay, so what I'd like to do is get into the real juicy stuff now. This is kind of a tipping point where we start to take a closer look at the digital components, the creations of logic gate artisan level. You know, when you're building electronics, I got to tell you, there's a part of it that's science and there's a part of it that's artistic. And whenever you have, and this is just a philosophical point that I'm making here, you might say that martial arts, there's a science to martial arts. There's a very technical aspect to martial arts, even though arts is in the name, right? So when you're looking at Oriental methods of self-defense, or any method of self-defense, martial arts, and there's one out of Israel that's really garnering a lot of attention. It's a more modern form of self-defense. Krav Maga, I think, is the name of it. And then there's a Brazilian style where there's a lot of cartwheels and flipping and stuff, right? In any case, there's elements that are very technical, and there's an awful lot of science in the mix, even though there's a lot of creativity and art. Whenever you have an intersection between technology and science, and it's blended with aspects of creative and artistic pursuits, I would like to think of this as a formal discipline. So when I think of the term discipline, if computer architecture is anything, I would define computer architecture as a formal discipline, meaning that there are creative aspects and there are they're also very methodical, very orderly, very meticulous, scientific aspects to this, right? And you've experienced some of that meticulous stuff already. Any questions about my remarks in that regard? Now, in terms of the learning objectives, we are going to modify this. I'm going to update this because what I'd like to do is, well, I'd like to enhance the last objective. So it says design a complex logic gate using 3 or more different components that must include NOR, NAND, XOR, and XNOR. You might think, well, this is kind of like deja vu. In a manner of speaking, it is. By the end of this semester, what we're doing is making more room for the latest, greatest stuff in the last 2 modules in particular. You'll notice that the read and view assignments are still in the same early chapters of the textbook, but we want you to take another pass at section 2.2.2 and 3.1, 3.2, because as you go back and you review that same material, having the benefit of these other new understandings, other new components, right? We're extending what we know about a MUX, and we're going to be exploring something called a digital flip-flop, right? So at this point, we're going to reach a tipping point where logic gates to this level have always engaged a specific discrete function without the element of time or sequence. Now, this is very important to understand. Up until module 3, the completion of module 3, the logic gates we have investigated perform a discrete specific function on demand as needed, right? But there's no element of sequence or time or automation yet. And this is the tipping point in this entire discipline where the landscape changes dramatically, where the world as we know it becomes possible, where we, within a few short life cycles, we have all of the digital environment that we know and enjoy today. All of that happened at about this point in time, where the pioneers of electronics realized that they could actually work sequence and timing issues, a clock. Has anyone ever heard of the term system clock?
Yes.
Yeah, system clock, right? Can everyone see my screen?
Yes.
Okay.
Yes, we can see it.
So the other exciting part of this to me is that in this module, in module 4, and we're only going to introduce some basic concepts. We will stop in about 10 or 15 minutes and use the rest of the time in our class session to assist and to work one-on-one with folk to resolve any assignment or solution challenges that are still in the mix for your previous modules. But what we want to do is plant some serious seeds today. We want people to get the idea that now we're looking at matters that pertain to the physical sciences, physical materials used for electronic logic gates, right? So we have virtual logic gates we've been working with in our simulated environment. However, the world's first logic gates were not created in a virtual environment. They were actually created with physical materials. You've already been introduced to some very basic logic gates that were built with nothing other than a light bulb, a battery, and a wire. Which two logic gates am I referring to? Anyone? For which two basic logic gates can we make out of wire, battery, and light bulb?
And an or.
And an or is correct. Thank you very much. And an or. So as science and physics and engineering, electrical engineering have progressed, what they discovered is that there are some compounds that basically, and the term is transistors. There's layered material, and if you attach a set of wires or pins, you can create the behavior of an electric circuit to duplicate many of the logic gate functions, especially and or, and not. So originally, your grandparents, or actually maybe at this point in time, your great-great-grandparents, they used to gather around a radio. I don't know if it was kind of like a family thing to do at night, just like we gather around streaming media series that everybody are addicted to. Before that point, people were addicted to radio programs that were carried over electromagnetic, there was electromagnetic energy that was blasted with an antenna, and it was called AM radio, right? So when we get into digital communications and networking in the spring semester, we're going to be talking about AM and FM, right? Frequency modulation and other types of multiplexing. We have basic transistors, and those transistors were used to build the first radios and the first TV sets, right? So these primitive logic gates basically allow electrical and electronic engineers to start pulling together large numbers of those logic gates, and those large numbers then become capable of doing very elegant things. I refer to the casino scenario that we just talked about, right? We don't have a whole lot of ands and ors in the mix in order to do some pretty interesting things in a hypothetical scenario at a casino or for gaming, right? So you can just imagine what happens if you keep building from there. One of the things that you have to understand, though, is that there's this huge dichotomy, and by that I mean there are two different worlds. In the materials sciences, they hit a brick wall, and there's a difference between an engineering approach to integrated chips and transistors that used a method known as TTL, and there's another one called CMOS, okay, or CMOS. These are older, so the TTL is older and CMOS is more current, and we'll get into more specifics about all of that on Friday. In any case, you've often heard of silicon and silica, and basically if you take a certain a more pure version of beach sand, there's a more pure version of beach sand that's actually mined with large trucks, and they load up dump trucks with a higher grade of beach sand, and that's called silica. And what you're going to engage in this module is a great deal of additional information online. There's going to be a lot of YouTubes, right? So here's an interesting video that explains how it's processed. I want you to get a head start of this. As soon as you finish your first attempt of module 3, I want you to queue these up. And yeah, You can skip the Grammarly commercials, of course. So this is the Intel channel, and yeah, there's a version of beach sand, right? Now this is all of 2 minutes. Please, I'm just asking you at this point in time, please, if there is a link in our study guide, I intend for that to be there because it's important. Take the 2 minutes to click and watch it before you continue, okay? This is going to be a kind of a modus operandi for modules 4, 5, and 6. You're going to have a whole lot more independent stuff to review. That said, inside here in module 4 in references, can everybody see my screen?
Yes.
Okay. You see here, cool videos on digital components, courtesy of Real Engineering, the Learning Circuit, and Element 14. We really need you to dive into the references folder. Remember that if it's in the references folder, the intent is that you learn it well. Resources provide additional options to kind of pursue additional information at your leisure, but if it's in the references folder, it's critical information. And I know we're in the habit of scouring our study guides and addendums. There will be an addendum for this. I'm in the process of drafting an addendum for module 4, so you'll see that under here. But take the time to get in here and review, because what these videos provide is an alternate or extended opportunity to get under the hood in addition to the study guide. So I talk about a flip-flop here, digital flip-flop, right? We revisit MUX and DMUX. So we talk more about MUX and DMUX and how it really was a revolution. So we planted a seed last module, and now what we have is a case where we have the additional concepts you need to know and understand about MUX and DMUX, and we want to refresh that trail and dive a little deeper. When we talk about a digital flip-flop, you'll often hear the term latch, okay? So when you're watching videos and you're diving deeper into flip-flop, essentially flip-flops are a required component of system clocks. So when you get to the place where you have timing and sequence capacities or capabilities in your digital components, whenever you have timing or sequence capabilities in your digital components, somewhere in the mix is a DFF, okay? A flip-flop, a digital flip-flop. And it's this digital flip-flop that also makes another ingenious invention called the memory. Everybody knows what random access memory is, right? Has everybody seen, has anyone seen a memory module at least? Had their hands on it or viewed it or understand what I'm talking about?
About RAM, right? Can you just
Talking about RAM.
Mhm.
From our von Neumann model of computer architecture, random access memory is constructed of memory chips. On a very microscopic level, you have these digital flip-flops in the mix, and it allows for, as long as there's energy, as long as there's electricity, as long as there's a cycle, as long as there's a repeating sequence, we can get a digital value in ones and zeros, and we can, with each clock cycle, refresh those digital ones and zeros. It's the ability to refresh, and as long as the power is running, as long as we keep refreshing the combinations of ones and zeros, those ones and zeros remain intact, in a manner of speaking, you could say they are stored in that memory module. And then once the power is cut off, there's no more refresh, and the ones and zeros eventually fade. So this ingenious invention is really one of the key components that changed everything, changed the entire landscape. And embedded inside RAM modules, in this case, dual inline memory modules. DIMM stands for dual inline memory module. There's a set of pins on the bottom of the circuit board that allow for a connection to the motherboard. And the memory chips are hard soldered into this circuit board. And it's these pins, gold-plated pins. Yes, there is gold. Gold-plated pins and copper. So there's a lot of precious metals in the mix. And at one point, you could actually like melt CPUs. You could melt computer chips, early versions or early generations of computer chips, and extract the gold. It's a lot of work. It was a lot of acid, very toxic, not good for the environment, but but basically, and that's the disclaimer. So don't grab old computers and start tossing them in acid baths thinking you're going to make it rich. You're going to strike it rich. But there's a lot of precious metals along the pins here, and that's how it connects into a slot, right? So it's a memory slot. You'll notice that each of the modules has an offset, a little notch here. This one is for a laptop. This would be called a SODIMM. It's a smaller form factor. The notch is in a different place. So it's quite common for different generations of memory modules to have slots in a different place, right? You see the difference here. Previous and newer generation, you have the slot. That means that you can't use or interchange memory modules with newer and older motherboards past a point, because the physical notch is there for a reason. And there are so many different bits. This could be 32-bit RAM and this could be 64-bit RAM. I want you to notice, and I'm just generalizing here, but you notice that this module has much greater number of pins compared to the module on the top, right? Any questions about memory modules and what we've talked about here? So is anybody into crystals?
No.
No. Did anybody study rocks or minerals?
I got crystals.
Yeah, as a part of earth science, right? Or as a part of certain hobbies, crystals are a big deal. And there is literally a crystal that's embedded in the function of a system clock. When subjected to forms of energy, crystals will create what's known as an oscillation. It's a repeating pattern of waves that is very consistent. So you'll have an oscillation of so many thousand hertz or so many thousand cycles for a given second. And it's this crystal that becomes the basis, the tick behind and there's hundreds or thousands or millions of these oscillations for each second. But crystals are used to create the physical component that clocks need, system clocks need, in order to keep time. And so this is another piece of physical science that's really fascinating in terms of how it's evolved. And crystals, you can actually build an AM radio out of crystals. So if you want to go back and do some interesting research in early electronic components, you could build what was known as a crystal radio. And it was actually a thing that Boy Scouts or 4-H clubs would do, if you're familiar with 4-H. One of the telltale signs that a DFF is in the mix is that there's an inset triangle. What do we mean by inset triangle? If we look at this diagram here, Can everyone see the rectangular outline here of this digital component?
Yes.
Okay, so this is like the interface view, not the implementation view, but the interface view. The interface view shows input and output, and then you have this loop, right? And there's an equation that goes with that logic gate function. So you have one input, one output. You have a rectangular outline for the logic gate diagram, but what you see right here is like a piece of triangle or a teepee or a tent, right? If you were to cut a triangle out of the bottom center of that outline, that's what we mean by inset triangle. So if you notice a logic gate that has this taken out of the side, that's a sure giveaway that you're dealing with a digital flip-flop. Okay. You've heard of multiplexers, right? So MUX and DMUX. Everybody remember MUX from last period, from last module?
Yeah, sure.
Okay. So this is something I want you to study, and I want you to become one with this diagram here. If you have a MUX and combine it with a DFF, what you get is your first rudimentary, very basic, very crude, but it works, something called a memory register. At the basic level, this is what all digital, random access memory is composed of, right? So a memory register is like a subatomic or atomic component. Registers become the building blocks of memory modules, and memory modules in terms are hard soldered to the dual inline memory modules, the circuit boards, right? So at the most basic level, this is how we build a memory register. This is it right here. And what would our world be without memory? Could you store digital information in a place where you could work with it? Could you store instructions on what to do, what calculations or computations you would apply to that digital memory? Could you have a place where the initial results for those first steps, those first calculations, could be stored as intermediate results? None of that would be possible unless we had kind of a workbench. That's why we refer in our von Neumann diagram to memory being like a workbench in a workshop. It's the memory that allows us to store digital information and the instructions used to compute with that digital information. This is it right here. This is where everything changed. One of the components that changed our world forever, right? And I know I'm being melodramatic, but I think it's worth a little bit of time to share how simple yet elegant, how I just get all misty when I think about the art and the science that went into this discovery. It's the stuff of legends, right? And the people who did this, oh, they're dead and gone now. I mean, they're in the ground. But our world is so different because they figured out this little combo right here. So for what it's worth, I just wanted to reach this point in the Module 4 study guide. And what I'd like to do is stop sharing and stop recording, and then use the remaining time to assist if students have any requests for some of the challenges they're still working on yet. Does anyone have any questions or comments about the material we've covered to this point?
Yeah.
Yes, question.
I wanted to speak to you after this. Yeah.
Certainly. Any questions about the material we've been covering in Module 4? Going once. Going twice. You should see, when you refresh your connection to Blackboard, you should see the module 4 in Blackboard is now available. Please dive in, have fun. And as you start to investigate, everybody should have a sense for what this little bad boy is right here. Yeah. What am I looking at right here? What is that? What is it shaped like?
That's or.
It's shaped like an oar, but there's like a very prominent open circle on
That
the
is nor.
It's a NOR, right? So, I mean, take a look at this, right? You have a NOR, you have a NOR, you have wires that are crisscrossed. It's flip-flop, right? Wow. And then, so this is the first piece. And then the second piece is that memory register, right? Take a MUX, stitch it or tack it onto a flip-flop in a certain way, and voila, first memory register. I hope that you dive in and I mean, here's one about transistors and how this worked, right? PNP and NPN. We'll get into that more later. We haven't talked about the CPU yet, but the CPU wouldn't even be possible if we didn't have memory in the first place. And memory wouldn't be possible if we didn't have a logic gate that allowed us to drive a sequence, a cycle, a clock, where we can order and organize computational statements against some digital information, right?